For differentiation, one of the most important way of solving a sum would be using chain rule. Now in chain rule, let's take an example. If I have y, that is combination of two functions such that one function is inside the other. So if I say it is f of sum g of x, so I have a function inside a function of x. So let's see, if I say y is equals to, if I have log of x square plus 3. Now in this case, my x square plus 3 is a function and this log is another function. So I have two functions, one inside the other. What we do is we take the inside function and we name it as t. So here if I say my x square plus 3 will be equal to t, then I can find my dt with respect to dx. So if I differentiate this, I am going to get 2x. So we can say my dt by dx is nothing but 2x. Now I can substitute that t in y and I can say my y is equals to log of t. We can solve or we can differentiate this y with respect to t. I can say my dy by dt becomes 1 by t. And if I need to find dy by dx, we can say it is dy by dt into dt by dx. That will give us 1 by t into 2x. If I substitute t, we get 1 by x square plus 3 into 2x. So this is how we can solve using chain rule. This particular function will be called as chain rule, where we substitute one value or one function of x which was inside another function. Now you can skip the substitution part and directly solve this as well. I can say, first of all, when I have y is equals to log of x square plus 3, so first I will differentiate log, and we know for log differentiation is 1 by x. So my dy by dx should be equal to first differentiation of log, assuming this particular part is t. So I'll say 1 by 1 by x square plus 3, and then finally differentiating this t part, that becomes 2x. So we get the same answer. So this is what is called as chain rule, and you can do it as many times as you want. If a function is inside another function and another function and another function, you can basically keep on doing this. You can keep on differentiating one function and then inside function and then inside function, and basically you can multiply them together. This is called as chain rule. Let's see a few examples. In the first one, we have two different functions. One we will say this function and the other would be this whole raised to 5. Now traditionally we should substitute this as t and then do our dy by dt and do our dt by dx, but we can do it together. We can say our dy by dx should be equal to, now we can say first we will do this t raised to 5. So for this t raised to 5, I will get 5 times t raised to 4, or we can say our x square plus 2x plus 3 whole raised to 4, and then we will multiply differentiation of this t. Differentiation of t becomes our 2x plus 2. So this is how we can write our final answer. This becomes our chain rule. Now for the second one, we have y is equals to log of 2x cube minus 5. Here again you can see this part is one function and log is another function. So I can again name this as t. When I differentiate dy by dx, I can say first I will differentiate log t, that will give me 1 by t, or you can say 1 by 2x cube minus 5, and then we will differentiate this 2x cube minus 5, that gives us 6x. So we get this becomes our answer. If you want you can simplify, if you want you can write them together, however you feel. Then this third one, for the third one, now we have three different functions. We have four different functions. We have this x square plus t, then we have log of that, then we have cube, and then we have e raised to. So we have four different functions here. So for that what we can do is, first our dy by dx, first we'll integrate the outermost function, that becomes e raised to. So for e raised to x, we know differentiation becomes e raised to x. So we'll say e raised to whatever was there, instead of x we'll just write log of x square plus 1 the whole cube. Then we'll go to the next function. The next function would be our cube function. So for x cube, we know it is 3 times x square. So we'll say it is 3 into log of x square plus 1 the whole square. Then we'll go to the next function, that is our log. For log it becomes 1 by x, or here we can say 1 by x square plus 1. Then we'll have to differentiate that x square plus 1. So I'll just write it here, into we'll have 2x. So this becomes our final differentiation. So you can go on and on and find differentiation, or you can use this chain rule to find differentiation if we have function inside another function and inside another function, and you can go on and solving it this particular manner. Let's solve some sums that you might find in your examination. Now for the first one, if you see here, we have three kinds of functions. One, we have x plus 1, then we have squared, and then we have e raised to x. Now these two functions, x plus 1 and then squared, these are basically one into the other. We'll use chain rule to solve them, but total e raised to x is multiplied to this function, so we'll have to use that multiplication rule. So when we differentiate, we'll say our dy by dx should be, first we'll use multiplication rule because they are multiplied together. So we'll say first e raised to x constant and differentiation of our x plus 1 whole square with respect to x, and then plus we'll differentiate our e raised to x keeping our x plus 1 whole square constant. Now our e raised to x is as it is. Differentiation of x plus 1 whole square, we'll use chain rule. So for that we'll assume our x plus 1 to be our t, and we'll differentiate t square. T square should give me 2 times t. So into, I'll get 2t, instead of t I'll write x plus 1. And then I should differentiate my t being my x plus 1, and differentiation of x plus 1 should give me 1. So into 1. Then plus x plus 1 whole square is constant, and differentiation of e raised to x should give me e raised to x. Now if you want, you can take your e raised to x and x plus 1 common, and you will get 2 plus x plus 1, or you can say finally it is e raised to x plus 1 into x plus 3. So this is how we can find our final differentiation. Now let's see the second question. In the second one, again we have maybe 4 different functions. First we have this log of x, then divided by we have our squared function, then we have e raised to x plus 1, and then we have 2x. So we'll go one by one. First we have that division, so therefore we'll use that division rule. So we'll have dy by dx. The division rule says that we'll differentiate our u first, keeping our v constant. So we'll have e raised to 2x plus 1 whole square. Differentiation of log x should give me 1 by x, and then minus I should differentiate my v, keeping my u constant. So when I differentiate my v, first I should differentiate, I'll write it down, I don't have enough space there, so I'll write it down here. My dy by dx should be, first differentiation of log x, I should get 1 by x, keeping v constant, that becomes e raised to 2x plus 1 whole square, then minus differentiating our v, so we are going to get first differentiation of squared value, so it will be 2 times e raised to 2x plus 1, then differentiating the inner value, that is e raised to 2x plus 1, so differentiating that, e raised to 2x should give me first e raised to 2x, and then I should differentiate, plus 1 will be 0, so then e raised to 2x I should differentiate it again, and I should get 2. So this becomes my differentiation of that e raised to 2x plus 1 whole square. Now we will keep our log x constant, so ln x, then upon the whole upon we will keep our v square, so that becomes e raised to 2x plus 1 the whole square. Now from here you can take your e raised to 2x and 1 e raised to 2x out of these common, and you can remove it from here, and we'll say what we have left is 1 by x e raised to 2x plus 1 minus 2 into 2 will have 4, so 4 e raised to 2x log of x upon e raised to 2x plus 1. So this becomes our final answer. For the third one, again we have multiplication rule first, this into this. Then for the first one we have two different functions, we have 2x plus 7 and we have raised to 4, and for log we again have two different functions, we have actually three different functions, we will have log, then we will have squared, and then we will have 4x plus 3. So for our third one, our dy by dx will be, first we'll have multiplication rule. So for multiplication rule we'll differentiate first and then we'll differentiate the second one. Now if you want you can do it separately. So I'll do it separately first. So I'll say differentiation of my 2x plus 7 raised to 4 with respect to x should be equal to, first I'll differentiate raised to 4, so that gives me 4 into our 2x plus 7 raised to 3, then I'll differentiate 2x plus 7, that gives us 2. So this becomes our differentiation of that. Similarly I'll do the differentiation of our log 1. So differentiation of log 4x plus 3 whole square. If you are wondering y log is written as ln. Ln is nothing but natural log, that is log to the base e. So many times you might find in books, in question paper, they have written ln, that is nothing but log to the base e. And for throughout our course, whenever we see log, that is also default as log to the base e. But in our calculators, you should always make sure that log written is log to the base 10 and ln is log to the base e. Now we'll get back to our differentiation. So differentiation, first we'll do log differentiation, so it should give me 1 by, we'll have 4x plus 3 whole square. Then we should do square, that is going to give us 2 times 4x plus 3. Then we will do 4x plus 3, that will just give us 4. So these are the two different differentiations. Now we'll use our multiplication rule. So we'll have our dy by dx. Using our multiplication rule, we know that we'll keep our second constant, that will be ln 4x plus 3 whole square constant, and we'll differentiate our 2x plus 7 raised to 4 with respect to x plus, now we'll keep our 2x plus 7 raised to 4 constant, and we'll differentiate our log 4x plus 3 square with respect to x. Now we can substitute both are our values. Now we can take our 2x plus 7 whole cube common from both of them. We can take 8 common from both of them. We can remove one of the 4x plus 3 from here. So we'll have 8 2x plus 7 whole cube common. We can say we have ln 4x plus 3 whole cube plus, we'll have 2x plus 7 upon 4x plus 3. So this becomes our final answer. Now I did a little bit of mistake. Where was the mistake? Okay, the mistake is here. I had log 4x plus 3 whole square. I wrote here log 4x plus 3 whole cube. So this should be square and this should be square. Okay, other than that I don't think there is any mistake. So by mistake I wrote square, I wrote cube instead of square. So this is how we will be able to solve our sums. Now we should take into consider some special cases. Now let's say if I have y is equals to x raised to x. Now we do not have any function where we have x raised to x. You might say these are combination of two different function where we have x raised to some constant, and other than that we have constant raised to x. Now these cannot be solved as a traditional differentiation. So for these kind of sum where we have function raised to function or such kind of questions, what we do is we use log. Now if I use log on both sides, I'll get log of y should be equal to log of x raised to x. Now we know for log the raised to part goes here, gets multiplied, so we'll have x into log of x. Now we can differentiate this. So if I differentiate both sides with our x, what we are going to get is we'll get log of y differentiation with respect to x and differentiation of our x log x with respect to x. Now I cannot differentiate y of or a function of y with respect to x. I should differentiate with respect to y. So I will say I will have here differentiation of log of y with respect to y into I'll have dy by dx. This is what we are trying to find. So I have multiplied and divide my dy. Now here on the other side, right hand side, I just have multiplication of two functions of x. So we'll use our multiplication rule. So for multiplication rule, we'll take our second constant, that is our log x, differentiate our x with respect to x, then plus we will have differentiation of log keeping x constant. Now on the left hand side, differentiation of log y with respect to y should give me 1 by y into we'll have dy by dx, and here we'll get our log x plus x upon x, or we'll just get 1. Now we need to find only dy by dx. So I'll multiply my y here, so I'll have y log of x plus 1. Now I can substitute my y. My y was x raised to x. So we'll say it is x raised to x log x plus 1. So this is how we could find our dy by dx when y was not a traditional value. I'll take another example. Let's say we have y is equals to x raised to x raised to x raised to x, and this is going on forever. So there is no limit. I'll just write it down here. Y is equals to x raised to x raised to x raised to x, and this is going on forever. So for this kind of a sum, we'll use our again the same rule. We'll just take log on both sides. So we'll get log of y should be equal to our log of x raised to x raised to x raised to x, so on till infinite. So I can say this is nothing but this whole power will come down, will come and be multiplied here. So I'll have x raised to x raised to x raised to x raised to x, and so on, multiplied with our log of x, which I can say this part, our x raised to x raised to x and so on, is nothing but our y. So we get y log of x. That becomes our log y. Now we can differentiate both sides. Again we'll differentiate with respect to x. So we get our log y differentiate with respect to x should give us differentiation of y log x with respect to x. Again I cannot just differentiate y with respect to x, so I will write this as differentiation of log y with respect to y into dy by dx. And here again we'll use multiplication rule. So for multiplication rule, we have log x constant differentiation of y with respect to x, then plus we will have y constant differentiation of log x with respect to x. Now here we get 1 by y dy by dx, and we get log of x dy by dx, plus here we'll get y by x. Now what we can do, we can take our dy by dx on the same side. So we'll have 1 by y minus log of x dy by dx give us y by x. We can substitute it back. So our final dy by dx becomes y by x divided by 1 by y minus log of x. Now in the solution you might find y being substituted and written as x raised to x raised to x, and here also x raised to x raised to x, but you can recognize that. So this becomes our final answer, dy by dx. So there might be some cases where you might have to use log to actually find that. I'll take one more example for this kind of a question. Let's say I have something like y is equals to x root x root x root x, and this goes on forever. For this again, what we'll do is we will assume all of these values are basically y, because if I remove this part, my first x root x, still this is nothing but our y, because it is going till infinity. So I can say that this is nothing but my y is equals to x under root of y. Now using this I can write this as y upon under root of y is equals to x, and I can say my y is nothing but 1 under root of y is equals to x, or y becomes x square. So I am getting y in terms of x. Even if we do not get y is equals to x square in this traditional manner, what we can do is we can differentiate this by assuming we have x is equals to under root of y, and now we are differentiating our x, so we are finding dx by dy by differentiating our y. So differentiation of, we'll have y raised to half with respect to y, and this is nothing but our half y raised to half minus 1. So you can say this is 1 by 2 root of y, and that is nothing but our dx by dy. So our dy by dx should be equal to 2 of under root of y, and if you want you can substitute your y, so that becomes 2 of under root of x root of x root of x, and so on. So these are some wild questions that they might ask that have a special way of solving. We substitute our y. In the previous questions, you might say we substituted all of these values as our y, and then we solved it. Similarly, or you can say here, we would have got y is equals to x raised to y, and then you can solve it. You can take log on both sides and solve it. Similarly, in this one, we are assuming all of these values are also giving us y, and we make this equation and we